select few that have been able to make it this afternoon. I think you're going to hear a very interesting and enjoyable talk. From someone who I've got to know very quickly in the last 15 minutes. Iain has told me virtually his whole career life history, and it matches...
Not very long.
Not, perhaps not, but it's interesting to me anyway. He started off working in nonlinear optics, in organic nonlinear optics, on a project that I was involved in way back in the late 80s into the early 90s. And that was at Hertz-Solanese in the United States. Following that, he transferred to Merck, where he stayed until very recently moved to Imperial College. And his interests have been, as I understand it, in organic nonlinear optics initially and organic electronic materials more latterly. And I think today you're going to be talking about organic electronics and FETs.
Yeah.
Over to Iain.
Well, thanks very much, and thank you for coming along today. I know it's absolutely freezing, so I don't think I'll be able to heat you up. I'm sorry about that, I can't help you there, but we'll try and keep things moving at least over the next 45 minutes or so. Graham's right, I'm going to talk about particular organic transistors, organic thin film transistor devices. I should start off by really acknowledging the group at Merck. So I've only been at Imperial College for about 4 or 5 months. I joined there from industry. I've spent all my career in industry, 20 years since my PhD, working in various areas of organic materials for optics and electronics. And I was the manager of a research group at Merck involved in the design of organic semiconductors, mainly polymer materials, for transistor applications and photovoltaics applications, and a little bit of OLED work as well, but not too much. And we had a lot of collaborations, but I think I'm only going to show data from, of course, from our group, but also from the NIST group in Maryland in the US, and Palo Alto Research Center in lovely California, especially nice on a day like today. So actually, I think I have a couple of slides for anybody that's sort of wandered in that's not familiar with the area at all, and I'll try and go through those quite quickly, just a sort of overview of what organic electronics is and why people are interested in it and what it can do. And then I'm going to start talking about transistors to switch displays, the active backplane, active matrix backplane in displays, and in particular the semiconductor component of this transistor device, and what it does, how we can optimize it, and from a molecular design perspective, what the important design criteria are in trying to improve the performance. I might skip over this depending on the time, talking about ink formulations. I think we had sort of brief discussion about this earlier today. What type of rheology is required to inkjet or flexoprint or spin coat, and how we can try and achieve this combining polymer materials and solvents. And then I'll talk a little bit about what's important for the future in terms of commercialization, but also in terms of the technology and the science. Okay, so this device is a transistor, organic transistor, or any transistor really, and so it's comprised of the following parts. You have a substrate here in sort of grey colour, and this can be for flexible materials, can be PET, polyethylene terephthalate, PEN, polyethylene naphthalate, but sort of first generation are actually stainless steel with an insulated coating, so a very thin steel coating. Then you have an electrode here, source and drain electrode, and these are printed or lithography defined. On top of this you then deposit in red the semiconductor, and to give you a feel for the dimensions here, this is called the channel length, and this is typically about 1 to 10 microns in length, depending on the complexity and cost of your printing step. So if you use lithography, which is expensive, then you can get to very short channel lengths. And if you use something like gravure or flexo, which is much cheaper, higher throughput, you pay the penalty in resolution. You can only achieve maybe 50 nanometer channel length. And just skipping to here, why that's important is that the frequency of the device is proportional to the inverse square of the channel length. So the longer the channel length with the same mobility, the lower the frequency of operation. So on top of the semiconductor you have an insulator dielectric layer. This, I should mention, isn't drawn to scale. Typically this is maybe about 100 nanometers thick, and the dielectric might be 1 micron or so thick, so this is a much thicker layer. And then you have a gate electrode which basically switches on and off the device. And one of the features here that's important is that this gate should be registered with respect to the channel. So you want this right over the top, and if it's too far to the sides or if it overlaps too much with the electrodes, you get capacitance effects that affects the IV characteristics. So you want to have a well-defined gate, and you want to have it more or less registered over the device. So this modulates the current that flows along. Basically, so you have a bias or a voltage across source and drain. In the semiconductors, typically in the off state, you then sweep the gate voltage, you introduce a negative bias for a P-type device. What happens then is that the holes that are either intrinsically present in the semiconductor or injected from the source form an accumulation layer between, I'm kind of shivering here, it's not easy to sort of focus this beam. So just basically between the semiconductor and the dielectric here, you get the accumulation layer. And you see this depicted here. This is the IV characteristics. So this is the source drain current. This is the gate voltage. You see here it's very low, so there's no current flowing between source and drain. You're sweeping the gate voltage more negative, and then at a particular sort of threshold or turn-on voltage, then you get a large increase, large modulation in current. And so when you look at this IV characteristics, you want high on currents, but you also want a good sub-threshold slope. So in other words, a large change in source drain current across the device with a very small increase in gate voltage. And so probably the most important application for organic transistors is in displays. And I've shown here a very simple active matrix backplane circuit. So basically your rows and columns, you have your transistor here. The transistor charges a storage capacitor, and that's in parallel with the pixel itself, which is this sort of purple colour. So what's important also in these backplanes is that once you've charged the storage capacitor and the transistor's off, then there shouldn't be a leakage pathway back through the transistor. So you want a very low off current. And that's why a lot of organic materials are not suitable, even good organic semiconductors are not suitable for backplanes, because this off current is too high. And this storage capacitor discharges too readily. You can't really see it here, but this is basically an LCD 3-dimension. So you have your polarizer, you have your small TFTs that are used to switch the LC layer, and there's colour filters and another polarizer, and it's quite a complicated device structure. So what I'm showing you here are some prototype displays that are out there at the moment. This is probably the most interesting. This is a product that's coming out this year, although caveat is that they have been saying this for the last 2 years, but I do believe it will. But it's early days in 2008, so you can boldly say this at the moment. Come November time, it might be a different story. But it's a spin-off from Philips called Polymer Vision, and it's actually quite nice and impressive. This is a real image here. So this is a video of a working display that's rolled up and down. It refreshes maybe a few hertz. It's not very quick, so you can't show video in. It's also monochrome, and I think this is probably slightly larger than A5 size, not quite A4, but it's very thin. And this is it here. The actual display that they're going to produce for Italia Telecom is not a fully rollable display. It's a foldable display. Plastic Logic in the UK, although they're going to manufacture too much consternation in Dresden in Germany, have this product here, which is a bit larger size. It's an A4 e-book, e-paper type module. And the hope here is that this can do for PDFs what the iPod did for MP3s or whatever format Apple used. So they, really to try and you see if you go onto Amazon right now, they're selling an e-book. It's called Kindle or something like Kindle. But it's rigid and the content's not quite there yet. You can't put every paperback on it yet. But once the content becomes more readily available, I think this technology might really take off quite nicely. And this is actually an LCD. So this is an XGA 15-inch, quite high resolution prototype from Samsung. It's a couple of years old now. You can see a couple of lines are out here, but very nice display. And the motivation here is to replace amorphous silicon in an LCD. So the first displays are these electrophoretic displays that are going to be commercialized. So what I'm showing here is a sort of time to launch or expected time to launch axis. And this is the mobility of the semiconductor that's required for the transistor to drive the backplane. And so, as I mentioned, that previous Polymer Vision movie that you saw there was an electrophoretic display. It's a reflective effect, so the colour, as the brightness, ambient brightness increases, the contrast increases in your display. So it's basically what happens is that this transistor here can be more or less the same size as the pixel. So this is a cross section of the device here. This is your transistor and this is a display effect. So the ambient light comes in, it's reflected. This is your media, which is little microcapsules of pigment that's switched by the electrical field to either black or white. And because these transistors can be large, then the output requirements per unit area are a little bit lower, so the mobility requirements tend to be the order of 10 to the minus 2. It's also bistable. Once you've created this image, in other words, you've applied the voltage and you've moved the pixels physically from either the front of the media in liquid to the back, then they more or less stay there. So it's it's not very power hungry. As you start to move towards something that's maybe more commercializable, thinking about things like large area signage or even full color, high performance, then the resolution requirements become very similar to LCD, greater than 0.1 or more. And this is the type of thing to have in mind. You've seen these two already. This would be, for example, the type of advertising sign that you might find in an underground station that's typically maybe changed once a week at the moment. If you could change this 10 times a day, you could imagine much larger revenue, and also you could target the display to the particular audience that's in front of it. I mean, imagine the type of people that are standing on a railway on the underground station at 7 o'clock in the morning are probably different from 9 o'clock in the evening. So you could certainly sort of target your advertising. So it's quite an attractive idea. This is an AMLCD. The big difference here is this is a transmissive effect. So the light is coming through from the backlight through the pixel. So because the transistors are opaque, you only want them to be in a very small corner of the pixel. Otherwise it's blocking the light and reducing the power efficiency. So the transistors are very small, and because they're small, the performance requirements are a little bit higher than the equivalent electrophoretic display, but typically around 0.5 or so for amorphous silicon at the moment is good enough to drive most AMLCDs. The attractive feature for organics about AMLCD is the technology exists today. You know, liquid crystals are everywhere. Liquid crystal displays are all over. They're cheap. And one of the ways to make them cheaper would be to change the electronics from silicon-based technology to organics. You've seen that before. But probably the sort of holy grail for everybody is an all-printed display. In other words, integrating organic transistors, the sort of circuitry with the emissive component, moving towards an OLED display. This is further off, of course, and the mobility requirements are a little bit higher, around 1 centimetre square per volt second. The sort of technology and the requirements are sort of converging a little bit, because requirements are coming down as the efficiency of the emitting component goes up, and at the same time the performance of the organics are always going up the way, so we're sort of meeting each other in the middle. And already you can see a lot of prototypes where organic devices are driving OLED displays. One big difference here is that even though this is not a transmissive effect and the transistors can be quite large, generally because you have more than one transistor per pixel, then they can't be as large as the equivalent electrophoretic display where you can just have one transistor which can be a little bit larger. I mean, there are other big differences here with an OLED display where the output is directly proportional to the current. So in other words, if you have 2 pixels and the transistor A is twice as high performing as transistor B, then the brightness in pixel A will be twice that, or more or less, as pixel B. So device to device uniformity tolerance in an OLED display is a lot tighter than in a field driven display effect like a electrolytic display, where you have a threshold that governs the image. So this is again one of the big differences. And there are a lot of prototypes out here. This is, I think, Samsung, and this is Sony. This is a flexible OLED that's driven by organic transistors. Not that impressive. This is on rigid substrate, but again it's organic driving OLED. So what's out there at the moment? What's the sort of state of the art for organic semiconductors? So talking a little bit earlier about some options here. This is a pentacene precursor, quite an old material now. And basically it's a way to solubilize pentacene. You do a Diels-Alder reaction with tetrachlorobenzene here. You form this puckered ring structure that's a lot more soluble. You spin cast this, it's still like a glass. You then thermally treat it to do reverse Diels-Alder and removing the precursor. And when you do that, you form this typical sort of herringbone crystal motif that's common for pentacene. And mobilities are pretty high now for this solution process material. Another way to prepare small molecule devices is to start off with, again, a soluble pentacene, but this time don't remove the precursor, just actually use it to prepare your crystal structure. So what this is doing, you have these they're called triisopropyl silyl acetylene groups in the 613 positions. And what they do is they force a sort of slip stack packing, 2D slip stack packing, where you get the face-to-face arrangement. So this is looking side on at these pentacene rings. This is one acene, this is another. So the side units actually dictate the crystallization and the packing in an optimum way. And this way you get a very nice packing for transport, and mobility is really very high. In fact, I've seen mobilities of over 5 with a different oligoacene, which we've been working on at Merck and other places. In terms of semiconducting polymers, there's a whole range of polymers. If anybody's interested, there's a list of citations here. This is one that we've been working at here at Merck. We've also worked on regioregular polyalkyl and other thienothiophenol polymers and arylamines and other classes of materials. Mobilities have been able to reach above 0.5, and the latest results from NIST group with this material here, using a high work function metal to reduce contact resistance. I think it was platinum. They were able to get charge carrying mobilities of over 1, with this particular material, which is PBTTT. And this is going to be the material that I'm going to talk about now, probably for the next 15 minutes or so. So when we think about how we're going to design polymer semiconductors, we take a lesson from high performance small molecules. And what you see clearly here is that crystallization, organisation, long range positional order is very important. And so what we've been trying to do with these polymer structures is to make very crystalline ordered materials. So we try and planarise the backbone to get this pi-pi stacking, so that the pi-pi distances are 4 angstroms or less. So we have to pay particular attention to the conformation. And in regioregular polyhexylthiophene, what I mean by regioregular is that the alkyl chains are projected in a head to tail arrangement with respect to neighbouring thiophene units here. And also you see that these sulfur groups are arranged in an anti-configuration. And this is optimal for intermolecular arrangements. Moving to this new class of phenothiophenes, and I'll talk a little bit about this later, you see that the persistence length or shape is a little bit different. It's more of a sort of crankshaft approach. And what I'm showing here is the thermal behaviour of the polymer. This is a DSC, so this is the heating endotherm, cooling back down, and the crystallization exotherm. And you can see here, this is a very sharp crystallization, and that's again indicative of a very crystalline material, pure material, narrow polydispersity, and high degree of regioregularity. And when you sort of play around with this shape, backbone shape, then you see that you can really depress the melt point and depress the crystallization point. There's other reasons why we put the 2,3B unit in place, and I'll talk about that a little bit later. But one other feature about this material is that it's regiosymmetric around the phenothiopene, so there's no issues about regioregularity. So this is a symmetric repeat unit. This unit is also symmetrically repeat unit. In this case, the backbone is a little bit more regular in shape, not quite as linear as P3HT, but the conformational freedom is reduced because, again, we've fused these thiophene units together, and this actually helps to charge carrier mobility. Other differences here is that the physical distance between the alkyl chains is larger than in the case of P3HT. I'll talk about I guess the reasons or the influence that has on properties later. But also it's a regular spacing, whereas in the case of PBTCT, you see you have this irregular. On the one hand, you have a short spacing and a longer spacing here, shorter spacing here. So there are things you can do, and they all play an important role. In this case, in the PBTTT, because we have this regularly spaced alkyl groups and the spacing is large enough, we can get interdigitation from neighbouring units, and this gives rise to ordered side chains. In this case, it's disordered. And when we have ordered side chains, we have two thermal transitions. We have a side chain melt and a main chain melt, and we're calling the region in between side chain, between these two transitions, a liquid crystalline phase. It's more or less true. And when you process in this liquid crystalline phase, you can take advantage of the lower viscosity of liquid crystalline polymer materials in the melt phase, and this allows this self-assembly to occur. So the annealing step is much more efficient, and so this gives rise to improved properties. This is PBTTT. If we look at the the way that this packs together, this is a side view of the backbone. It's almost perfectly planar. The alkyl chains project at an angle, but quite interestingly is that you form these lamella where the backbones pack, and this is the pi-pi distance. But even though the plane of the lamella is in the substrate plane, so if you imagine this is a substrate along this line here, these lamella pack in the plane of the substrate, even though there is a tilt angle of the backbone. But when the second, so this is one lamella, and this is a sort of a lamella above, the alkyl chains from one lamella to the next interdigitate. and this gives rise to this highly ordered structure. And you can probe this structural order by X-ray scattering. In this case, this is grazing instance. So if this is your film, your incident beam is almost in the plane. So it's probing this order here, so you can get this what they call 0-1-0 reflection, which is a pi-pi reflection, and you see it's very sharp. I mean, a typical polymer looks more diffuse, kind of like this. This is more or less van der Waals distance, but here you can see sharp peaks. Specular X-ray diffraction is the opposite. You're coming in more or less out of plane to the film, so you're probing the distance between the lamella, the D spacing if you like, and you can see this is a 1-0-0 reflection, again very sharp. And you see higher order reflections. Again, this is indicative of a highly crystalline film. And the fact that there's no mixing here between the out of plane and the in plane reflections. So in other words, there's no 1-0-0 reflection in the in plane, and there's no 0-1-0 out of plane. Shows that these lamella are also very well oriented, so there's no sort of misorientation of the domains. And you can also see this from spectral ellipsometry. So again, you're probing here the absorption coefficient in the plane. So if you imagine the long rod, the optical axis is in the plane, so the absorption is pretty high in the plane. Whereas if you look at the out of plane absorption, there's absolutely no absorption at all. So you see that these conjugated backbones are more or less completely in the plane of the molecule, whereas P3HT, this is regirregular P3HT, which up to a couple of years ago was the benchmark organic semiconductor. You see a significant out of plane absorption, so you get this misorientation that's occurring. And there's been some publications. This is quite a nice one from the NIST group, 2007, Advanced Materials. And what people are starting to discover is that this whole order and organisation is really dictated by the side chain interdigitation between the lamella. And in the case of P3HT, it had never been done before, but if you just do a very simple calculation of the sort of close packed density that these alkyl chains would need to have if they were interdigitated, depending on the angle that they project from the main chain. And you assume a D spacing because you know that from X-ray studies. What you see is that no matter what the angle is, if you go to 0, so this would, 0 angle would be normal to the backbone, and 90 degrees would be in the sort of the same vector as the backbone. You see here, of course, as the side chain folds down, the density becomes even higher. But even when they're sort of fully extended, the density here, the close packed density, is higher than the density you can calculate from crystalline polyethylene, which is probably about as dense as you're going to get for alkyl packed chains. So it's sort of very, very unlikely. Whereas in the case of the red here, sorry, the blue here is PBTTT. You see here that at an angle of about 45 degrees, you approach the side chain packing density of linear polyethylene. And actually, you know, when you do polarized IR measurements and other measurements, you can predict this side chain angle, and it does fall almost exactly at that number. So the type of densities we do achieve with this material are really as high as we can get. This work actually came out very recently in Macromolecules, so it's no longer a manuscript in preparation. It's out now. yeah, this is the terracing effect. So if you look at the topography along this line here, you see it's, you know, dark colour going from the sort of darker brown to the yellow. Is it this region here? You see this basically steps up, goes back to the brown, so you're back down here, back to the yellow, back up, and then it goes into this even darker region, which is a two-step down height difference. And this height, this is nanometer scale, as I mentioned, is related to the, or is equal to the alkyl chain length at the angle of which is projected. And you see when you move from C12 chain to C18 that this step height is larger. Not quite so well defined terraces here, so the noise is a bit more, but yeah, quite nice. And you see this is a histogram of heights. So, well, all this is almost esoteric. I guess we were looking to try and make transistor devices. So what's the electrical performance like? And again, we're able to achieve very high mobilities. This is a bottom gate device, so silicon, silicon oxide, gold electrodes. Typically we have HMDS or OTS treatment. Again, this bit to promote the organisation of the semiconductor. And we get these, you know, nice transfer characteristics, good output characteristics as well, and the details are shown here. A lesson for polymer chemists is that, you know, if you make a polymer material with a number average molecular weight of 8,000 and the performance is not so good, don't give up. It could be that in fact you just need to improve your polymerization process and move to a higher molecular weight. You see here that, you know, this again is a thermal characteristic, same polymer, PBTTT, low mobility, one thermal transition, quite low temperature transition. As you start to increase number average molecular weight, performance, you know, jumps a little. You start to see almost like evidence of two transitions here. You've moved from this one-dimensional whisker-like morphology where you've got these almost like wires where the width of the wire equals the length of the chain. So you've got, you know, you don't have two-dimensional or three-dimensional order. This is sort of hybrid structure, moving again to these very high ordered systems. You have two transitions and much higher performance. One of the big problems with polymer semiconductors is solubility, and unfortunately everything we try to do to improve the solubility has an adverse effect on the performance, and this is a sad tale as shown in this slide here. You reduce the order of the material, you do improve solubility. In this case we're also trying to improve the ambient stability by lowering the HOMO energy level, but again performances were never that great. And so I'll get to the second point, is trying to achieve higher ambient stability. And what I'm showing here is one of the primary redox reactions that occur. This is an electrochemical, so it's a thermodynamic electrochemical process that occurs in the presence of a polymer. So polymer is oxidized, loses an electron, in the presence of oxygen and water. So this is a sort of forward two reactions that will occur. And this is an exothermic process when the ionization potential of the polymer is around 4.9 to 5 electron volts. That's in when you assume you've got a saturated water environment. So it really depends on the relative humidity here. But basically, if you have an ionization potential of less than that, you've got to be a little bit worried that you're going to have oxidation in the presence of water, or the combination of water and oxygen. So what can we do to push this ionization potential? So if you just look at the energy diagram here, the ionization potential is defined as the energy of the HOMO subtracted from the vacuum energy. So if you want a lower lying HOMO energy level, then there are some tricks as chemists you can do. And I guess this is a physics department, I won't go into this in too much detail, but you can play around with conformations to stop the intramolecular pi orbital overlap. You can change the electron density of the backbone. You can change the conjugation length, and you can play around here. And there's a nice paper by the Phillips group that shows why this is important. But of course, if you push this down too low, you create this barrier to charge injection, and you also lower the mobility. And so this is a problem. It's very much a trade-off. So we started playing around with a variety of thiophenes-containing materials, in which case we were able to quite nicely tune the ionisation potential over quite a wide range, but unfortunately mobilities were never that ecstatic. Typically you saw this depressing trend that as you started to increase ionisation potential, you lowered the charge carrier mobility. But when we started looking at these thionyl-thiophene polymer structures, we were able to shift again this ionisation potential to higher. This is a UPS spectrum with the binding energy. You see here that we've increased ionisation potential by 0.25 volts, electron volts. And the reason we're able to do this is because this is more aromatic. It stops through conjugation, not completely, but a little bit. And also there's no electron donating alkyl chain, so again the electron density is a little bit lower. And so this is more stable, and you see this that when you expose P3HT to a combination of ambient conditions, you see this is the transfer characteristics. Immediately quite nice, low off current, sharp turn on, reasonable voltages. But when you move to a couple of days in ambient conditions, this off current is increased orders of magnitude, and it's hard to switch off. It's very doped. And you can imagine this is not ideal for display. Whereas in case of PBTTT, over a similar period, slightly longer, you do see this increase in off current, not quite so dramatic, and also threshold voltage shift, but again not quite so large. So we're on the right track, not perfect, but much better. But interestingly, when you clean up this air, originally we thought what we were doing was we're just removing the water from this whole redox equation, and here for 72 days you see pretty reproducible transfer characteristics. So in a low humidity clean environment we get a nice transistor performance. Yeah, I thought I had another slide on this. But I have this inverted commas clean, and what we're starting to think is that in fact that this is due to the sort of pollutants in the atmosphere. It's more due to ozone and nitroxides than it is to moisture. So in fact you could operate devices in ambient conditions if you remove ozone and nitroxides. But eventually found one where we had, in ambient conditions, almost completely reproducible transfer characteristics up to, we could have kept on going, I guess, but at this point we sort of proved our point, that it was very, very stable. And again, if we look at Specula X-ray diffractions, you see these very sharp peaks. You actually even see them from an as-spun film. So, if you look at these semiconductor materials, as I mentioned earlier, they're not that soluble. But in fact, they could be what you're forming as little microaggregates, almost like nano dispersions, and that when you spin them, you've already got structural order. And it seems to be the case in this case anyway. There's no annealing required. You just drive off the solvent, or you can blow it off at ambient conditions, and you get, highly ordered, good mobility materials. So I did have another slide on this. So if you compare top and bottom gate architectures, this is a bottom gate architecture. In this case, the semiconductors completely exposed to ambient conditions. In this case, you've protected the semiconductor with this dielectric in the gate. And it's hard to exactly compare because you need different dielectrics in both cases. But in this case, in a bottom gate device, you see, after a few 90 days or whatever, you see big differences in the off current. Orders of magnitude jump up. So it seems to have doped quite a lot. A little bit more hysteresis, not looking quite so good. But in the case of the top gate device, it's not identical, but it is pretty good. You know, there's not a lot of difference after 55 days with this particular polymer. And so people used to think, well, it's because it's just a simple barrier to oxygen. But these are organic dielectrics, you know, and if you think about diffusion over the course of 55 days, oxygen and ambient moisture are clearly coming through. Even, you know, P-dot gate, Teflon or some type of PMMA type dielectrics, they're not going to be a barrier here. So what is proposed these days is that this is actually like a sacrificial layer to the highly reactive pollutants. And there's quite a nice paper by Michael Shabanik that came out last year that he's looked into this in a bit more detail, because you know, the electron affinity of ozone or nitroxides is much larger than oxygen, so they're much more reactive and much more likely to dope or be a cause of doping. And so if you can protect this, you can get much improved performance. I'll just talk for another 2 or 3 minutes and see what happens to run out of slides. Talk about dielectrics for a minute or two. These are organic dielectrics that people are starting to use. In this case, we've got a bottom gate device, an organic dielectric, organic semiconductor, in this case a top contact source and drain. This work is from the former Avisia group that was bought by Merck. This is Janos Ferris, in particular Simon Ogier. So Simon's just moved to the PTEC centre up the road, or down the road, or across the road, or up the road. So at Wilton, where ICI formerly were. Actually, I think it's well removed from there, but it's the group from CPI and CNAPS that are forming this. So Simon is one of the physicists who's going to be setting this whole process up. And what they proposed was that you need low-K dielectrics for high-performance organic semiconductors. And they made an argument on the basis of energetic disorder at the interface. So if you have a high K, you have high polarity at this interface, and what they're showing here is sort of density of states. And if you have, they're showing that at the bulk and at the interface is broadened by this dipole effect, and making quite a convincing case. In the case of polytriarylamine, this is mobility, and this is the dielectric constant of the dielectric layer. You see here this relationship is quite a strong one, that the highest mobilities are with very low K dielectrics, which causes its own problems, because low K dielectrics have low surface energies. Low surface energies are very difficult to spin coat on. And also, if you think about it in terms of capacitance, for low voltage operation, you really want a high dielectric constant semiconductor. So this observation is really not optimal, and people are starting to think about bilayer, sort of 2-layer dielectrics, high K for switching voltages, and then maybe a low K treatment to improve the density of states at the interface. And there's also a scaling effect. You can't make the channel length too small without also having to decrease the dielectric thickness. So that's another reason why, you know, there's a lot of interest in very thin dielectrics. That if you want to go to ultra fast switching speeds with very thin channel or very short channel lengths, then you have to also scale your dielectrics. And this is shown in one case. Oops. I didn't realise that this was animated. So in this case, you have in one device where you've got, you know, a longer channel to thickness device, in this case LED, is much shorter, then the sub-threshold region is not so good when you've got too thick a dielectric with respect to the channel length. You know, it's harder to accumulate the charge, it doesn't switch on, sub-threshold regions not so good. And before anybody freezes, I think I'll more or less stop there. I've only one more slide. Acknowledgement of chemicals, a lot of third-party funding that we had in Europe and UK and in Germany. And thank you for your attention over the last 50 minutes.
Well, thank you very much, Iain, for a very interesting talk indeed. May I just open the question briefly?
Of course.
The polymers that you've been describing, you talk about mobility all the time.
Yeah.
Are we talking about intrinsic conductivity, and so basically electrons and holes here?
No, this is field effect mobility, which is different, I guess, even from time of flight mobility in a couple of ways. One would maybe be the field dependence, and the other is the vector in which transport occurs. So I'm talking about in-plane two-dimensional transport at Highfield. Bulk transport, which you measure by time of flight, which is more sort of important for OLED or photovoltaic devices, is an out-of-plane transport. So if you think...
Can we consider, can we be thinking in terms of electrons and holes in this material like we do in conventional semiconductors? That's really...
Well, yeah, I mean, these materials will conduct electrons, not quite so easily. There was a paper by, I think it's Peter Ho, who's now moved to Singapore, and Henning Seringhaus and Richard Friend and the Cambridge guys, that showed that, well, I mean, it was pretty, I think it was clear that this was the reason. So that they basically had a silicon dioxide dielectric, which they would then treat completely with a hydrophobic alkyl silane, and that they remove the traps. And if you remove the traps, then you get electron transport in most of these organic materials. I think that the electron transport was maybe 1 or 2 orders of magnitude lower than the hole transport. That's not the case in time of flight measurements. In time of flight, hole and electron transport for even thiophene materials is quite similar. I mean, there is other reasons why a field effect device, so that the way you inject the charge in a transistor, you have to inject it from the electrodes. So if you have a barrier, or if you have, you know, maybe a high work function electrode, it's hard to inject electrons. Whereas with time of flight, you're photo generating the charge, so there's no issue of injection barriers. So you can see the electron transport much better by time of flight. But these days there are quite efficient solution processable electron transporting organic semiconductors with, you know, very high electron affinities. So they typically tend to have cyano functionality, fluorinated functionality, anything to withdraw the electrons away from the conjugated system. So there's a company called Polyera that's spun out from Northwestern University that sell these materials, and other groups that work on them.
Okay.
Quite a long answer.
I guess I'm taking up too much time. Any more questions from anybody else?
There's a lot being said recently about these low-K dielectrics.
Yeah.
But the problem is, most of them are like PTFE.
Yeah.
Right? So you try and put something on the top of PTFE, it don't stick. So how are you going to stop delamination in your...
Okay, there's a couple of things you can do. First thing is that you can get polymer materials to stick to PTFE. There are 2 or 3 ways you can do it. The most destructive way is you treat it with like a oxygen plasma or corona or some type of very destructive exposure that changes the surface energy, changes the chemistry at the surface, introduces hydroxyl, carbonyl, acid functionalities, and, you know, increases the surface energy. You don't want to do that, of course. I mean, especially if you have a bottom gate device where you're then going to put a semiconductor, you've introduced all these traps and your device is rubbish. there are treatments. I think there's a company in Oxford that has treatment layers for fluoropolymers. There are other solution-based treatments that Merck have been involved in. I can't talk about too much. So there are approaches to solving that problem. You're just introducing a sort of interlayer between the Teflon-like material and the gate. There are other groups that actually don't use a solution deposition technique to deposit or print the gate, in which case they have more success to put down the gate as well. So the question remains about adhesion, delamination. That's a problem in not only in that layer, but your organic semiconductor is not exactly a high surface energy either. So, I mean, one way that people, they almost like spot weld these devices. So you create these areas of very high surface energy outside the device channel length or the active area of the device, where you can get high areas of adhesion. So even though you have low adhesion in the device, in the overall architecture, it's only small parts of the overall area that are poorly, have poor adhesion, and other parts of high adhesion. So that's one way to try and solve it. But yeah, I mean, it's a major problem.
Do you have any idea of how much higher the mobility could go in the coming years?
I don't think that. So if you think about, for example, single crystal rubrine has a mobility of about 20. I can't see that being beaten with a solution deposited material. I mean, I mentioned that you can get mobilities. I think that I can say this because Steve Tierney at Merck at the moment mentioned this, answered the question at a plastic electronics meeting last November, and his comments were printed in the Syntelic newsletter. So this is not proprietary information. So Merck do have materials that he mentioned that have mobilities of over 5, I think was the number he quoted in his talk. But I can't say too much about that, obviously, because it's proprietary to Merck when I was there. So there is some hope that you can get, but that's not the real problem. The real problem is not really, although you have a mobility of 5 in the lab, and by the time you manufacture, you introduce the fabrication compromises that you need to do, you might end up with a mobility of 0.5. So you've dropped an order of magnitude as you go to high throughput production. Then you're at the cusp of you can do anything you like. But even now, with that type of mobility, it's enough to satisfy most first and even second generation ideas that people have for applications. That's not the issue. The issues have moved on to, what's device to device uniformity like? How do you print one layer on top of another? What's happening, when you, or how do you deposit from a gravure? How do you print from gravure formulation rather than an inkjet formulation, rather than a spin coat formulation? So the sort of focus is shifting a little bit. The race for high mobility is more or less irrelevant now. It's not the major focus. Mobilities are as high as amorphous silicon, maybe even higher. And some groups will say the threshold voltage shifts at gate stress are even better. So there's a lot of scope.
Is it only the polythiophene that are in this race, or are there any other?
Oh no, I mean I think that the small molecules that I showed you are even better. So if you where is it now? Seems like a long time ago. Is it? It's still cold enough though. So this was a slide I showed right back in the early days. This guy here, John Anthony, I think I mentioned this to a couple of people. So he has a nice Chem review article. Actually, this year or last year, he's a nice Angevanta review. It's either just came out in January of this year or December or something like that last year. So very recent review, and he shows very high mobilities with these type of small molecule structures, where you have this very highly ordered pi stacked, so face-to-face stacking. In this case, you've got face-to-edge type of order. It's electrostatically driven here, but here you've broken up the electrostatics with these bulky groups. So these materials are very high performing semiconductors, and there are other polymers that we'll be publishing in the next year or so that will show high performance as well.
Okay. Sounds like some exciting things on the way. Are there any questions? Mike?
Just on another mobility one. What are the prospects of getting a material or complementary materials where you've got similar electron and hole mobilities, then you can build up
CMOS.
sort of CMOS technology and emulate silicon?
I think that N-type materials are becoming important, not primarily driven by CMOS. Actually, I think these days most of the research is driven by photovoltaic development. So looking for fullerene replacements or even fullerene itself. So PCBM is a reasonably good electron transporting N-type material that you can buy from Celine and other companies. So you can do solution processed CMOS with that material. As I mentioned, there's the company Polyera and Tobin Marks and Antonio Fischetti's work at Northwestern University, where they make these perylene derivatives. There's also fluorothiophene derivatives that are electron transporting. A lot of groups actually are doing the electron transport with zinc oxide. So you can process zinc oxide at quite low. Zinc oxide's a really nice material, and it's becoming, I don't know if anybody is working on it, but it's worth taking a look at. You know, that you can get some fantastic devices with zinc oxide, and the processing temperatures are getting lower and lower. And so you could imagine a device where you can put down your N-type with your zinc oxide hybrid systems. So there are quite a lot of options.
Well, just one very quick one if anybody's got a last question. Yes, Andy, of course.
Well, it sort of sums up the whole talk. Everything you've done with the organics is driven to get the correct structural motif and ordering. You get the two-dimensional stacking to get the high mobility. Is that compatible with inkjet printing?
I think so. I think that because you have this liquid crystal, so for example with the polymer materials, because you have this liquid crystal mesophase, you can do a post-deposition anneal at low temperature for short times, in which you again develop the order and organisation. Small molecules, even with small molecules, I think you mentioned you met Mark James from Merck, who gave a talk last year at the Polymer Electronics Conference, and he showed some inkjet deposited data of small molecules. It's very, very promising as well. There, the trick I think is to have high boiling solvent, or at least a component of a high boiling, one component that's a high boiling solvent that allows I guess sort of somehow reduces the kinetically chaotic crystallization, nucleation process. So if you have a well-prepared substrate, again, you can treat that in such a way. I think it's definitely, I mean, it is possible. Then there are other problems though, maybe related to, as you know very well, things like coffee staining and other effects that solution deposition of printed small, high resolution structures bring.
I think we're going to have to work out what coffee staining means on another occasion.
Okay.
Thanks very much indeed, Ian, and thanks for coming.
Oh, you're welcome.